It's time for Exam 1 from Fall 2019 for MA 262. Let's get going. Question 1, we're solving this initial value problem here. Well, this is a separable differential equation. We have some function of y multiplied by some function of x over here. So what we can do is divide out y minus 1, multiply dx over, and we'll be ready to integrate both sides to get an implicit solution for this equation. So this will be 1 over y minus 1 times dy is equal to 2x over x squared plus 3 dx. Now we can legally integrate both sides. We end up with ln y minus 1 is equal to ln x squared plus 3 plus c over there. Then we will take e raised to both sides, and this always, the spacing always gets a little weird. There we go. And so if we do that, we can bring this c down. We can bring this c down in front because we could write this, as times e to the c, and e to the c is just a different constant. So I'll call that c1 there just to show that it's different. So then simplifying everything else, we get y minus 1 is equal to c1 multiplied by x squared plus 3, and we can add this 1 over, and we're ready to solve with this initial condition here for our value of c1. We're told that 9 is equal to c1 times 1 plus 3 plus 1. We'll subtract that. We get 8 here, 4 here, so c1 is 2. I'll replace that. And then we have our solution here. This is 2x squared plus 7. And if I get the correct answer key, yep, B is correct for number 1. Number 2, the general solution of this big thing right here is what? Well, we have a nice rational expression of y over x over here, because what we can do is rewrite this as dy dx is equal to, let's divide the numerator and the denominator by x squared. So we get x squared over x squared plus 3y squared over x squared all over 2xy over x squared. Simplifying this, we get a 1 here, and that doesn't simplify at all yet, and we'll get 2y over x down in the denominator. And now what we can do is our favorite substitution here, which is v equals y over x, which also comes with the fact that dy dx is equal to dv dx times x plus v. So let's perform that substitution. This will turn this equation into dv dx times x plus v is equal to 1 plus v squared, 1 plus 3v squared over 2v. Okay, let's subtract this v over and make that a v squared over v, and multiply the top and the bottom by 2 so that we get the same denominator. Then we can subtract that, and what do we get? We get 1 plus v squared over 2v right there. So now we have a separable differential equation, and I'll just rewrite this to be clear. We have v prime times x is equal to 1 plus v squared over 2v. And actually, since we're using the d's, dv dx, I really shouldn't have done that. Okay, let's move this over here, 1 over x, and then multiply the dx over, and then we'll move this guy over to the other side as well. That will give us 2v over 1 plus v squared dv is equal to 1 over x dx. Integrating both sides, we get ln 1 plus v squared is equal to ln x plus c Taking e raised to both sides, we end up with 1 plus v squared is equal to, and just like we did in this problem, we can bring that c out front of our e, and so this will end up becoming cx. So now undoing our substitution, we had that v is equal to y over x, so this is 1 plus y squared over x squared is equal to cx. And how can we rewrite this in the form that they're looking for? Well, this will be y squared is equal to cx cubed minus x squared. Is that what they are looking for? No, it looks like they want the x squared on that side, so we can just move that over, and we get exactly answer choice C for number 2, which is correct. 3, a tank containing 100 gallons of water with a salt concentration of blah, 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 blah. Okay, so it's one of these salt tank mixture problems. Our equation for this every single time is dq dt plus r0 over v of t times q is equal to ri ci. And we'll start filling in these values here. It's good to note Q is just the total mass of salt in our tank at any given time. Okay, so what are all of these values? Well, R0 and Ri are the rate of outflow and the rate of inflow of the mixture into our tank. So we see that we have a salt mixture entering our tank at 2 gallons per minute. So that can go in the rate of inflow little box. And the well-stirred mixture is pumped out at 1 gallon per minute. So that's our rate of outflow. And since we started with 100 gallons of water, our equation for V of t, our volume of our tank as a function of time, well, how's that going to change over time? We started with 100 gallons. Water is entering at 2 gallons per minute and leaving at 1 gallon per minute. So every minute we gain 1 gallon in our tank. So 100 plus t will give the number of gallons in our tank as a function of time. Now the concentration in, which is our last thing to fill in, is just 2 pounds per gallon. So this side will become 4. Now to solve this for Q of t, we can use integrating factor, where this is our value of P of t, that's 1 over 100 plus t. And our integrating factor, rho of t, is equal to e to the integral of P of t dt, that is e to the ln 100 plus t. We drop the c, and we can simplify this down to 100 plus t. Now, then the method of integrating factor says that our solution is given by Q of t is equal to 1 over rho of t multiplied by the integral of rho of t times q. Oh no, well, this is what we would call Q of t. This right-hand term, I'll call it z of t dt. We don't really want to overlap with what our solution is called. So let's fill in these boxes. Rho of t is 100 plus t in both cases. And z of t is just this right-hand side, which is 4. Okay, so integrating, what do we get? Well, Q of t is 1 over 100 plus t multiplied by 400t plus 2t squared plus c, and this is Q of t. We have an initial condition here, or at least we should. So we know that, yeah, we're told that initially we have 100 gallons of water in our tank with a salt concentration of half a pound per gallon. That means that our initial quantity of salt in our tank at t equals 0 is 50, because we have half a pound for every gallon. 100 gallons, that's 50 pounds. So applying that initial condition, 50 is equal to 1 over 100 multiplied by c. So this is c over 100 is equal to 50, and 50 times 100 is 5,000. So we'll plug that in for this c, plus 5,000. 1,000 there. So at this point, all we need to do is plug in Q at 50. We're looking for the amount of salt in our tank after 50 minutes. So Q at 50 is equal to 1 over 150 multiplied by 20,000 plus 5,000 plus 5,000. And this will give us 30,000 over 150, which is just 200. So E is our correct answer for number 3. Question 4, let's solve this differential equation here. Well, this is a perfect case for applying integrating factor because we have an equation of the form y prime plus p of x times y is equal to q of x. This is a linear first order equation here. And so we know that in this case our p of x is equal to negative 2 over x, and q of x is equal to x squared minus 1. And note that if there was any coefficient other than 1 attached to dy dx, we would have to divide that out in order to get things into this form right here. Okay, so integrating factor says we need to find our integrating factor, rho of x, which is equal to e to the integral of p of x, which is negative 2 over x dx. This gives us e to the negative 2 ln x, or just x to the negative second power. Now, finding our solution is as easy as setting up, what will this be? Y of x is equal to 1 over rho of x multiplied by the integral of rho of x times q of x dx. Let's plug these values in here. 1 over x to the negative second power is just x squared. Then this rho of x here is just x to the negative second, and q of x is x squared minus 1. We can rewrite this in here as 1 minus x to the negative second power, and we are ready to integrate. This will give us y of x is equal to x squared multiplied by x plus x to the negative first power plus c. That does work out, right? Yep, that looks good to me. Okay, are we given an initial condition? No, we are just solving for y of x. So if we distribute that x squared, we should end up with one of these answer choices. And it looks like E matches that perfectly. So 4 is E. Question 5, which of the following is the implicit solution to this initial value problem here? So whenever you're seeing some really big terms like this, especially if they're parenthesed off like this and one of them is attached to dy dx, the other one isn't, and it's all equal to 0, especially when we see a big implicit function of y and x on the left side and then a constant on the right, you should be thinking, okay, this is an exact equation. But in order to check whether it's exact or not, we have to do a little bit of testing. We will label this function, or this expression here, m, and this one n, and we're checking if the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. My will be e to the x cosine y minus 2 sine x, and we're checking equality with nx, which is e to the x cosine y minus 2 sine x. So yes, this is an exact equation. Now at this point, all we have to do is take the integral of m dx and compare that with the integral of n dy, and we'll be able to pull our solution out of there. So the integral of m dx will give us e to the x sine y plus 2y cosine x minus x, and we're making a comparison between that and n dy, which is e to the x sine y plus 2y cosine x plus 3y. So now in order to form our solution itself, we have to note that we have overlap in all of the terms that include both a y and an x. So we only count those once in our final solution, but then we also have these two unique terms, which will also have to show up in our solution. So we can say that e to the x sine y plus 2y cosine x minus x plus 3y is equal to some constant. And since we're given an initial condition, we can solve for that constant. But it looks like, just looking at our answer choices, yeah, our answer is going to be C. And the answer key agrees. And often they will do this where the only correct left side of the equation, is your choice. They don't really make you they don't make you solve for that constant very often in order to ensure that you have the right answer, but let's do it anyway. Since y at 0 is equal to pi, anything that is multiplied by x, just straight up will go to 0. This is a 3 pi, and then these two are a little bit more complicated. Sine of pi is 0, and then 2 times pi times pi times negative 1. Did I do, sorry, cosine, it's the cosine of 0, so times 1, so 2 pi times 1 plus 3 pi, there is our 5 pi for C that we were expecting. Okay, sorry, that got a little sloppy in the end, but we figured it out. Question number 6, we have a Bernoulli equation. So this is an equation of the form y prime plus p of x times y is equal to q of x times y to the nth power, and we see that exactly here. Our p of x is 2 over x, and our q of x is 6x to the 4th power, and n is equal to 2. We have y to the 2nd power right there. So then we will apply this substitution. V is equal to y to the 1 minus nth power. So in our case, that's v is equal to y to the 1 minus 2nd power. So that's y to the negative 1. And that will end up transforming our equation into something that we can apply integrating factor to. Our equation will become dv dx plus 1 minus n times p of x times v is equal to 1 minus n times q of x. And this is something that you should definitely commit to memory. I never did, because these Bernoulli equations pretty much never come up on exams for MA 266. But it's much easier doing this than actually going through the entire substitution, especially when you're short on time in a real exam situation. So let's fill in these values here. Well, we know that 1 minus n in our case is negative 1. And our p of x, we said, is 2 over x. So right here we get minus 2 over xv. And then our q of x is the same q of x up here, which is just 6x to the 4th power. 6x to the 4th power. Okay, so now doing integrating factor, this is our new p of x term. And I'm calling it p of x because that's what we're used to talking about with integrating factor, but note that I'm not referring to the p of x that was originally up here. So p of x is equal to negative 2 over x. That means rho of x is equal to e to the integral of p of x. That gives us e to the negative 2 ln x, or just x to the negative 2nd power. And then we can solve directly for v. And I'm actually going to shrink a lot of this stuff down so that I have some more room to work. So solving directly for v of x is 1 over rho of x, so that's x squared, multiplied by the integral of rho of x times q of x, so x to the negative 2nd, multiplied by our q of x our q of x, which is just right here, minus 6 x to the fourth power. So in the end, we get minus 6 x squared dx. This gives us x squared multiplied by negative 2 x to the third power plus c. So now we can't solve for this c because we're not given an initial condition, but we also aren't done yet because we're still in the v world. We need to unsubstitute this, and since our original substitution was v is equal to y to the negative first power, we can write our solution as y to the negative first power is equal to, and I'll distribute this x squared because why not, minus 2x to the fifth plus c x squared. And then putting this in terms of y, we just have y is equal to 1 over negative 2x to the fifth plus cx squared. And that is B for number 6. And the answer key agrees. Let's consider this system and determine all of the values of the constant k for which the above system has no solution. So immediately, we're putting this into an augmented matrix. We have 1x1 plus 1x2 plus 1x3 is equal to 2. 2x1 plus 3x2 plus 2x3 is equal to 5. And 2, 3, k squared minus 2 is equal to k plus 3. Okay, well, we know that our we know that this whole thing will have no solution if we get some situation where we have 0x1, 0x2, 0x3 is equal to something that is not 0 on that side, because there's no way that we can add 0 of a couple different things and get something that's not 0. So we might just be able to solve this by inspection, because if we can well, actually, we'll do one step and then we'll try to solve it by inspection. So let's take row 2 and subtract it from row 3. That gives us a 0 here, a 0 here, a negative 4 there, and a minus 2, and a minus 2 there. So if k squared minus 4 is equal to 0, but k minus 2 is not, then our system will have no solution. So what if k is equal to negative 2? If k is equal to negative 2, we will get, our final line will be 0, 0. Negative 2 squared minus 4, which is 0, is equal to negative 4, which is an inconsistent statement right there. That's exactly the case that we were looking for. 0, 0, 0 is equal to something not equal to 0. And this is actually the only way to possibly get this. The other one that is pretty close but no good is if k is equal to positive 2. If k is equal to positive 2, we will get a 0 here and a 0 here. But this statement is perfectly fine. Our system will have infinitely many solutions where it's consistent, but that doesn't mean that the system overall will have no solution, because we don't have a non-zero number over there. So anyway, C is our answer for number 7. Oh, and sorry. Oh God, we're looking for the value of k for which the system has no solution. So k is equal to negative 2. Does that, not k is not equal to negative 2. Sorry about that. I hope that didn't confuse you. Just to reiterate, when we plug in k is equal to negative 2, we get 0, 0, 0, 4 on this final line, which is inconsistent. Sorry about that. Misread the problem. Number 8, if that is A, we're finding the values of x and y such that A times A transpose is equal to that symmetric matrix right there. So let's grab A. Our A is just 1, y, x, 2, and let's grab A transpose. A transpose will just reflect everything down the main diagonal. So our main diagonal stays the same, but we end up with an x over here and a y over here. Now multiplying A by A transpose, what are we going to get? We're going to get another 2 by 2 matrix, because this guy is 2 by 2, this guy is 2 by 2. These inner dimensions match. The dimension of what we get is these two guys right here. So 2 by 2 as an output. and how we're going to solve for these individual positions of our matrix. We'll call these A, B, C, D. We will get A by multiplying the first row of this first matrix by the first column of our second. We get B by multiplying these two together. And when I say multiplying together, I really mean taking the dot product. So for this one, we would multiply y and 1 and then add that to 2 times x. Then for our C and D entries, it's the same kind of thing, except we will be dotting these two, this row and column pair, and then this guy for D. So let's do that. Let's solve. We will get 1 plus x squared there. Y plus 2x. Y plus 2x and 4. Okay, wait, did I do something drastically wrong? Yeah, no, I did. It's not 4 here. It's y squared plus 4. Y squared plus 4. Okay, so when will this give us 2, 4, 4, 8? Well, if x is equal to plus or minus 1, we will get a 2 here. And if y is equal to plus or minus 2, we will get a 4 there. But I have a hunch that those negative values will not work for these guys on the off-diagonal elements, the C and D positions. So let's just try plugging in x is equal to 1 and y is equal to 2. We will get 2, 4, 4, and 8. Yeah, and you can test it for yourself if you use the other ones. If you use -1 and -2, yeah, we're going to get -4s here, which is not what we are looking for. So x is equal to 1, y is equal to 2 is our solution, so 8 is D. 9. The largest open interval on which the solution to this initial value problem is guaranteed to exist by the existence and uniqueness theorem is what? Okay, whenever you are given something like this, the first thing you have to do is divide out anything attached to y prime. So y prime plus t over t minus 4 times cosine t times y is equal to ln 5 minus t over cosine t. Now, let's grab a big number line down here. Note where our initial condition is in terms of t. That's t is equal to 2. And then I'll just circle this so we know it's our initial condition. And let's figure out where all of our kind of inconsistencies happen in here when we have some undefined behavior. So if t is greater than or equal to 5, then we'll have the natural log of something that's not a positive real number, which is undefined. So t is equal to 5 and on is no good. What about this guy right here? Well, when t is equal to 4, we get something over 0. So that's also no good. So t is equal to 4 is no good. What about these cosine t's? Well, cosine t evaluates to 0 for, pi over 2, 3 pi over 2, 5 pi over 2, etc. The only ones we really have to worry about are pi over 2 and 3 pi over 2. But 3 pi over 2 is greater than 4. So that's gonna fall somewhere over here. But all we're really looking for, and the reason that we don't need to really figure out where 3 pi over 2 lands if it's above 4, is that what we're looking for here is the longest distance that we can go to the right without hitting a discontinuity, and the longest distance we can go to the left without hitting a discontinuity. So that interval there will be the interval on which a solution is guaranteed to exist. And that is just between pi over 2 and 4, so 9 is A. And the answer key agrees with that. Okay, a Newton's law of cooling question. These don't come up too often, and they never come up in 266, so I'm not particularly familiar with these, but I worked through it before, so we should be okay. An object with an initial temperature of 32 degrees, so let's note that down, T of 0 is 32, is placed in a refrigerator whose temperature is a constant 0 Fahrenheit. And in this equation here, that is represented by Tm. So T subscript m is equal to 0. An hour later, so T at 1, the temperature of the object is 16 degrees Fahrenheit. What will its temperature be 4 hours later after being placed in the refrigerator? So we are told that T prime is equal to negative K times the temperature of our object minus the temperature of the thing cooling our object. And since that's equal to 0, Tm is equal to 0, we can just get rid of that. Really what we're going to be doing here is a little bit of integrating factor. I forget whether there's really an easier way to go about this. Yeah, but we could rewrite this as T prime plus kt is equal to 0. We can call our p of t term k and our q of t term 0, and just apply integrating factor where rho of t is equal to e to the integral of p of t, that's just k dt. We get e to the kt. So now solving for t of t, I don't like how the t's double up in this one. T of little t, so the temperature as a function of time, is 1 over that p of t, 1 over e to the kt, so e to the negative kt multiplied by the integral of rho of t, and that should be a rho, there we go, e to the kt times q of t, but q of t is just 0, so this whole thing is the integral of 0 dt, which will just give us a plus c. So there we go. We get c e to the negative kt. Okay, so now we can start applying our initial conditions to solve for both c and k. Since t at 0 is equal to 32, 32 is equal to c times e to the 0, so 32 is just equal to c. 32, there. Then we're told that t at 1 is equal to 16, so we can solve for that. 16 is equal to 32 e to the negative k. Dividing this 32 out, we see that 1/2 is equal to e to the negative k. Taking the natural log of both sides, the natural log of 1/2 is equal to negative k. We can move this negative over and apply a property of logs that I remembered yesterday, or had to for one of these exams, and turn this into the positive natural log of 2. And we see that that is equal to k. So now substituting that back into our equation, we see that t of little t, temperature as a function of time, is 32 e to the negative ln 2 times t. And we can apply that same process that I did a second ago. Get rid of that negative and turn this into a 1/2, taking the reciprocal of whatever was in that natural log. Okay, great. We are looking for the temperature of this object 4 hours after being placed in the refrigerator. That gives us T of 4 is equal to 32 e to the ln 1/2 times 4. And we can rewrite this, since we have a natural log in the exponent, we can rewrite this as 32 times 1/2 to the 4th power. 1/2 to the 4th power is 1 over 16. 32 over 16 is equal to 2. And there's our answer, B for number 10. Question 11, for what value of k is this vector in the span of these two other vectors? So we're not going to deal with row vectors here. We are this is a column vector only channel. So 2, 2, 1, 1, 1, 2, 1, negative 1, 3, 2, 1, and k. So we know that this third vector will be in the span of the first two if, when we row reduce them, we only get two pivots. So if our matrix is not full rank, so we're looking for two pivots, which tells us that these guys are not linearly independent as a set. Fine. So let's figure that out. Let's subtract row 3 twice from row 2. That will give us 0, 0, 0. Let's subtract 2 row 3s from row 1. We get 0, negative 1, and 1. I'll turn that into a 1, negative 1. Let's subtract row 1 from row 3. We get 0, 2. And let's add row 1. Let's add row 1 to row 4. We get 0 and k minus 1. So what's going on here? We kind of need to rearrange this to put it into a little bit more of an echelon form to get an idea of how many pivots we're dealing with at this point. And I will also parenthesis this guy off. Okay, so we see that we will get two pivots if we can use row 1 to set row 3 to be equal to 0. So let's subtract row 1 from row 3. We get a 0 here, k minus 3. And so when will this row be all zeros? Well, when k is equal to 3. Because when k is equal to 3, we get row of all zeros. We only have two pivots. That means that this guy can be formed from a linear combination of our first two. In fact, it will take 2 of these guys and negative 1 of this guy to form that vector if k is equal to 3. And you can go and write that all out, and you'll see that it is in fact true. And that means that that vector is in the span of the first two, if and only if k is equal to 3. And that's it. We are done with this exam. This wasn't too bad overall, except I still kind of don't like Bernoulli equations, and this was a little bit of a pain. But overall, not too bad, and hope this was helpful where you needed it.